That's the main thing. But this is a very complicated, because it's such a dense, one cell near the other, and suddenly there is a synapse here, there is a spine there, it's such a dense image. It's a very problematic image. It's very hard to cluster. Because this is the membrane, and this is the beginning of another one that comes from here. It's a real jungle, very dense jungle. But we know that this jungle is very hard or algorithmically to reconstruct the jungle of another.
By the way, just one question about the basic function is in terms of simulation. רציתי לשאול אם כאילו סתם מתוכן איזה, אם יש איזה תכנון הזה שאומרים לפעמים שעוד כך שנים אחרי שמסיימים גם לקח לזה לנסות לראות מעניין באמת כאילו פרודקטיבי נגיד לא יודע, זה מסתכל כמובן באיש של היום שעושים כל הדיפלר, מכיר כל הבייסיק שזה של המשין לנינג הרוב הזה שהתחיל על כמה זה באמת פשוט artificial viewing networks ויש עדיין שמשתמשים וזה מאוד מאוד גמיש ונמה ביצועים מאוד טובים. יש כאלה שעושים מהדברים הממש ענקיים, סגנון הדיפלר לקחת מאות מיליונים או כך וכך ולתת לזה דברים, אז למשל להביא לזה כל התמונות וזה ללמד בעצמו לזהות חתולים, לזהות עיניים והסגנון. זה באמת זה בייסיקלי קצת פרסופוני ועצמי.
מה שמנסה לעשות עם הבלו בריין, עם הקולום, יש פעם בנזון שמנסה ללמד את הקולום, לעשות פעולות כמו למשל ללמוד במכונית וירטואלית. אז ללמוד במכונית וירטואלית.
זה בדיוק את
ללמוד קצת להתמצא בתוך מקום נחשבים, נוחים, אמורות, וכך הלאה, ומנסים להכניס פלסטיסטי לגמרי לתוך הקולום, לתוך הסינפסות, כך שיבצע מטלות מסוימות. זאת השאלה שלך.
כן, זה באמת אני חושב שאיך זה לעומת החרדובית כמובן עכשיו.
כן, זה רק התחלה, כל זה התחלה.
Hi, everyone. Can you hear me on the microphone? Okay. I'd like to remind you that the exercise is due on Sunday because the Moodle was opened a few days late, right? So it's due on Sunday. If you need an extension, then you can ask for it, and there won't be any problem. Yeah, you can send by email. Your next exercise will be published probably tomorrow, and then you'll have 2 weeks to solve it. Okay, so today I'm going to continue speaking about bifurcations. And then once we cover all the basic bifurcations, we will move on to a topic called dimensionless analysis. And scaling. If we have time and we cover that too, then I will show you another applied model that will serve to learn many new terms. Yes? I don't think there is a control here. You can put the microphone farther away from me. לא. אם לא מילאת אז... Okay, so we already saw one type of bifurcation. That was the saddle node. Saddle node bifurcation. I use this as a shorthand for many words ending with shin. Now I showed you the normal form of the saddle node bifurcation. It was x dot equals r plus x squared. Of course, it can be also r minus x squared. So basically, every normal form can have pluses or minuses. It doesn't matter so much. So if you remember, this was a bifurcation where we had two fixed points. Because this function is parabolic, we had two fixed points. And as we vary r, these fixed points might come closer together. My drawing here is not standard. I don't usually draw curves for different r. But just to remind you, I'm doing it now. So the fixed points may come closer together. And at some point, they will merge one into the other as we vary r. And then they will vanish. And we kind of summarize this using a bifurcation diagram where the dashed lines represent unstable fixed points and the solid lines represent stable fixed points. And maybe it's better to draw the bifurcation curve in another color. So we'll know that these axes have no fixed points on them. So here we have two fixed points existing on one side of the r-axis and no fixed points on the other side, and we call this a saddle node bifurcation. I wanted to show you why basically any function, any system that has a saddle node bifurcation can be brought to this normal form close to the bifurcation point. This is the bifurcation point where the fixed points meet, and we call it RC, the critical R. So you can reach the normal form from any general system using the Taylor expansion. We have a general function f of x and of r, and we do an expansion around x star and RC, the critical R. So at the critical R, we have here only one fixed point. This is this curve where the fixed points merge. So the formula for
What value do we estimate things? Are we estimating now? Like,
what are we estimating?
yeah.
X dot. X dot. We want to see that x dot takes this form. Or actually f. X dot, which is f. The general function for a Taylor expansion around x star in RC would be this. Here we have an operator, the derivative operator. So inside these square brackets, there are derivative operators that act on the function f evaluated. First they act on it, and then we evaluate it at these points. And this power here means that you take higher order derivatives. So if this will be taken to the power of 2, we'll have this expression squared times the second derivative. I'm going to expand for the first terms, so you'll see what I mean. So x dot, first we take the 0 order term. So 0 order means that this is just like writing 1. So 0 order derivative is no operation. So we just evaluate the function at x star and RC. The first order terms have df. No, first they have this x minus x star times df over dx evaluated at x star RC plus r minus RC times df over dr, again evaluated at x star RC. Now second order terms. 1/2 x minus x star squared times the second derivative with respect to x, evaluated at the bifurcation point, plus 1/2 r minus rc squared times d squared f dr squared, evaluated x star rc. And then there are mixed terms, and then there are the third order terms. And I'm going to start canceling the terms here and see what I remain with. So the function evaluated at the fixed point is just 0, because it's a fixed point where f of x equals 0. This too is 0. Okay? So yeah, and this comes from the tangency of this function. So when the fixed points merge, the curve f of x is tangent to the x-axis. So its first derivative is just 0. Tangency. Okay. So the leading terms here that remain are this term and these terms.
You said about the mixed derivatives.
There are also mixed derivatives. But they should should actually go to 0. So our expansion leaves us with r minus rc times some constant value. Okay? We'll call it a, plus x minus x star squared, again, times a constant value. That's 1/2 times the second derivative evaluated at the bifurcation point. I'll call it b. And by shifting your coordinates, for example, defining a new x, say x wave equals x minus x star, you can reach this normal form. A and B, that's just calling this by another name. This is A. This is A. And 1/2 of this is B. This is B. Just for convenience. Yeah.
Can you explain again why is it 0, the tangency?
This one?
Yeah.
Here we have.
Where's the function? Which one?
So f is the curve. F is the curve that we are trying to expand around around this point. Okay.
How do we know that?
How do you know in How do you know in advance?
Yeah, we don't refer to this specific formula, right?
No. So this is something that you could do for a general function. Sorry, not a general function, a specific function. That say you are given a specific function, and you want to see whether it's it has this normal form or a different normal form. Okay, so then you would actually look for fixed points. Okay, so you can find a fixed point, and you can differentiate the function because you are given this function. You know the exact function. So you differentiate it, and you substitute. Okay, and you substitute x star, and you will see that this derivative goes to 0.
I'm giving an f. And how do I know that it has this thing that two fixed points merging together? I mean, it could be any f, right? How do I know that there exists such a x point such that
well,
the derivative of f in that x point?
so you can find fixed points based on the function, and you can see whether certain values of r give you only one fixed point instead of two. For example, r equals 0.
We use this function. We use a general function.
Yeah, a
Like
general
this is
function.
f,
Mhm.
right?
Yeah.
All right.
Okay. I think there is an example in the exercise. So try it. Ronen, yeah. Is the critical value of r. Yeah.
It shows to start on the second order of the extension.
Yeah.
We have another two terms
In the second order. Yes. So I can take them. So
And this is the first one. The first one you wrote, but you didn't wrote it on the left side of the word. And the second one you didn't with the mixed derivatives you didn't write at all.
I didn't write at all the mixed derivatives. So basically, you will have two mixed derivatives. One will be of the form this one, right? And the other one will be this one. Okay? So this goes to 0, just like this one goes to 0, right? So this goes to 0. So basically, since we know, okay, since we are dealing here with this type of normal form, this should also go to 0. But if, like I explained, what's your name? Itai. Like I explained, Itai, if you do this for an explicit function that is given to you, then you would actually take the derivative, and then if it's this normal form, then it might go to 0.
On the left side of the board, half r minus rc.
You mean this?
No, it should be
Plus terms.
plus terms r minus rc squared.
Plus this one.
Yeah.
Okay. Yes. You're right. Plus r minus rc squared. And I'll call this term, I don't know, this and this, like a g. Because C already appears here. Yeah, but Chagai, but I think you can assume that this is a lot smaller than this. It's not very significant here. Because it's squared. And we are very close to RC.
Oh, but it shows to take second order, so you need to report it.
Okay.
He doesn't have to take all the second order. Just some of the mathematics.
Yeah, in principle you're right. But it's obvious from this that this one is very small. Okay, this notebook. Okay, now I'm going to present other types of bifurcations. I won't show you how you can get to the normal form for each type. Maybe you'll do one in the exercise, but it's not very important. It's more important to know the types of bifurcations, to be familiar with the normal forms, You don't have to derive them, usually.
So each time I will have to find this special point, X and R.
Yeah, but you do it, a lot of times we do it using the geometric method.
So I just assume there is one.
Yeah, kind. Sometimes you don't know it numerically. So this is part of what we do in the course. We see how...
But I need to see that it exists, as you say, geometrically.
Geometrically, yeah. Okay, I'm leaving this on so you can have it next to the others. Okay, the next type of bifurcation occurs in systems where you always have your fixed points. They occur for all the values of the bifurcation parameter, but they might lose or gain stability. I'll start with an example, or actually easily brought to the normal form later. No, x times r minus s. So for example, x equals 0 is always a fixed point here. I'll start with the geometric methods. So rx minus x squared. So start with r negative. Okay. So when r is negative, then close to x equals 0, the linear term dominates, and we have a negative line function here. And farther away from x equals 0, the quadratic term dominates. So we have the curve decreasing like a parabola. So already we see two fixed points here, x equals 0, that's obvious, x equals r, and one stable, one unstable. Can draw the vector field. Okay, this is a phase portrait for r smaller than 0. R equals 0. Yeah, this is just minus x squared. So here we already saw this. It's a half stable fixed point. And no. And now for r larger than 0. So similar to before, next to x equals 0, this looks like a line. But farther away, it decreases like a parabola. Again, two fixed points, one at 0, one at r. Yeah.
Can you explain what's the goal and what are you trying to?
What we are trying to see how many fixed points this system has depending on r, and what are their stabilities. Okay, so this could be a physical system with some constant that represents a size of the carrying capacity of the environment, or other things. You'll see these things in the models that I will show. And you'd like to know for a given property of the environment or the cell that you're modeling, for a given property, is the system stable or unstable? and how many fixed points can it have. And what we are studying here is bifurcations. Bifurcations are the occasions where fixed points either appear or vanish or change their stability. So this type of system has a specific type of bifurcation that I want to show you. Okay, I'm drawing now the bifurcation diagram. Remember, this is x as a function of r, showing the fixed points as curves. So for negative r, we have a fixed point at x equals 0, and this fixed point is stable. So it gets a solid line. And the fixed point at x equals r. So I can draw the curve x equals r. This is just a line. It gets a dashed line because it's an unstable fixed point. Okay, for positive r, the fixed point at 0 is unstable, so it gets a dashed line. And the fixed point at x equals r is stable. So this is my bifurcation diagram. And this is different from the saddle node bifurcation, right? Here, there are two fixed points existing for any value of r, and it appears like they change their stability. So this fixed point is stable, but when we reach the bifurcation point, it becomes unstable. And this fixed point is unstable, and at the bifurcation point, it becomes stable. This is called a transcritical bifurcation.
Can you write on the diagram where the r is the positiveness?
Yeah? This is r equals 0. R is just the abscissa here. So this is positive r. There. This is a transcritical bifurcation. It's called transcritical because the fixed points exist on both sides of the critical point. So it's a transcritical bifurcation. They switch their stability between them. And its normal form is what we have there. X dot equals Rx minus x squared. Or it could be plus x squared. I'm moving on to the next type of bifurcation. This type of bifurcation exists in systems where we have symmetry. Symmetry with respect to x. And fixed points here tend to appear or vanish in pairs. Also because of this symmetry. So the normal form of this type of bifurcation looks like this. This can also be a plus, but for now we deal with this case. And I'll start by drawing the different cases. So first, the more simple case is r equals 0. So this is just minus x to the third. And we have a stable fixed point here. I just want to add that here we have a case where f dot of x at 0 equals 0. And this is one of these cases where we said you don't know the stability properties just by differentiating with respect to x, and then you need to do some further analysis. So what happens here is it's stable. We see by the geometric method that it's stable, but the interesting thing is that the decay into the fixed point goes like t to the minus half, and not an exponential decay. So it's slower than the exponential decay. The next case I'll draw, no, I want to draw first r larger than 0. So using the same consideration as before, close to x equals 0, the linear term dominates. So this looks like a line around here. But farther away from 0, the minus x to the third dominates. So these considerations give you a quick way of drawing functions that it's not immediately clear what they look like. So here we have 3 fixed points. 2 are stable, and 1 is unstable. Here, that x goes as t to the minus half.
What is t?
T is time. This is a system that evolves with time. X dot is given by this expression. So I just wanted to say that the function decays into the fixed point, not in an exponential decay, but in a slower decay. The remaining case, r smaller than 0. So again, close to x equals 0, the linear term dominates, and farther away, the cubic term is the dominant one. So again, a stable fixed point. Now, if we want to draw the bifurcation diagram, I'll use red again. So for a negative r, we have one stable fixed point. So it gets a solid line. For positive r, we have an unstable fixed point at x equals 0. So this is the dashed line. And two stable fixed points. It looks like this. So the normal form is actually easy to deal with analytically. So I can even get the actual expressions for these curves. If I take Rx minus x to the third is equals Rx times R minus x squared. So you see that x equals 0 is always a fixed point. Just a moment. And this can be broken down into x times square root of r minus x square root of r plus x if r is non-negative. So you see that you have here real roots for this equation when r is positive. These are these curves, and this is basically x equals square root of r, and this is x equals minus the square root of r. Yeah?
There's no interpolation for the imaginary part?
No. Because x is defined as real.
It's just real, so it's just drawing away.
Yeah.
So that way I get the imaginary part?
Yeah. So this is the third type of bifurcation that I show you today. It's called supercritical pitchfork bifurcation. It's called a pitchfork because it looks like a pitchfork. And it's called supercritical because fixed points appear when r is greater than the critical value. And there is a very similar bifurcation called a subcritical bifurcation, subcritical pitchfork bifurcation. So the subcritical pitchfork is just the other normal form. X equals Rx plus x to the third. Now I just want to add that the terms supercritical and subcritical, which I did not write here, subcritical pitchfork. The term subcritical or supercritical refers only to the sides of the plane where there exist more fixed points. So this is the direction of the pitchfork. If the pitchfork is pointing to the right, then it's a subcritical bifurcation, and if it's pointing to the left, if it's pointing to the right, it's supercritical, and if it's pointing to the left, it's subcritical. The stabilities of the different branches of the pitchfork, or its handle, do not determine the name of the bifurcation. So you could have a subcritical pitchfork where these branches are stable. It just depends on how you define your R. Okay? So the stability does not determine the term, the name of the bifurcation. Only the number of fixed points. Yes?
You said it's relative to y equals to the symmetry tree.
Yes.
Any intuition why you give any intuition for why it's relative for those terms?
Yes. The idea is that I can replace x with its opposite. So let's say I'll write it down here. I define a new variable y that's just equal to minus x. And I try to translate this equation to terms of y, and I'll get the same equation. Okay? And you see here that the behavior for a positive x and for a negative x is the same. Okay? Okay. We'll take 5 more minutes, and then we'll come back from the break a little later. Okay? Because I want to finish with this matter of the pitchfork bifurcation. I'd like you to notice the way that here, no, in the subcritical pitchfork, for example, we have here an unstable fixed point. In this whole region of the r-axis, there is no stability, and the system will just go to x equals infinity or minus infinity. And obviously, physical systems usually don't do that. They don't go they don't run away to infinity. If it's maybe a mechanical system, then you might have an equivalent thing where it will just break. But physical systems usually have higher order terms that stabilize them. And since we said we are dealing with symmetric systems, then we need to have invariance to the sign of x. And if I would like to write a physical system that would have a subcritical pitchfork but will be stable, then I would have to add a higher order term. So the next higher order term that preserves the symmetry that we talked about is x to the 5th. Okay? Now, this is a good opportunity to mention that when our system has positive terms, we can treat these terms as destabilizing. So when x is positive, the x derivative, the time derivative of x will also grow. So x grows with time. When x is negative, x decreases with time. This is why I need this term. So if x runs away and it reaches high values, then this term comes into play and it becomes dominant. And this term has a negative sign before it, which means that if x is very large and positive, then minus x to the 5th will be a negative value. So that x will decrease with time. This is a type of control that we have in the system. Yeah, this is stabilizing the system. And the bifurcation diagram for this type of systems looks like this. This will be r. This will be x. Now, we have these terms give us the subcritical pitchfork that we saw before. But this term introduces branches that will stabilize this part of the r-axis. Like this. So I have here two critical values of r. I'll call them rc. And here I want to call this rs. Because these two points are bifurcation points. Right? You know already the type of bifurcation. Right? A saddle node bifurcation. Saddle node bifurcations. So we have here a subcritical pitchfork and two saddle node bifurcations. And what this means is that when R is positive, the system can be stable on either of these branches. And I'd like to show you on this diagram an important property of dynamical systems that's called hysteresis. Hysteresis, which is, you could call it a path dependence. It means that the state of the system depends on its history. For example, if we start this system from a negative R, we have it stable at x equals 0. I'll draw this in green. Our system is stable. Now, if R is taken to be less negative, right, we remain at x equals 0. But if R becomes positive, then at this point, any small perturbation to the system will cause x to diverge from x equals 0, and it will eventually stabilize either on this branch or on this branch. So I can draw it like this, okay? Or maybe it should be a vertical line. So if I took R to be positive, then there was a small perturbation to the system, immediately I can no longer dwell at x star equals 0 because it's an unstable fixed point, and then the system goes into one of the other fixed points that exist here. Now say that I take R back to its original value. So I have here a stable branch. I can remain on this fixed point as R becomes smaller and smaller, and eventually as R becomes negative. So at this point, I have the same value of R as I had here, but the system is dwelling at a different state, just because the history was different.
Like having a different starting point, like x0.
Exactly, yes. And then I can take R to be more and more negative, and eventually this fixed point will disappear. It's a saddle node bifurcation. It will disappear, and we will return to the only stable fixed point that exists here, which is x star equals 0. So this path dependence is called hysteresis, and it's very interesting in physical systems. The last thing I want to say before we take the break is that this type of system is something that this general form with pitchfork bifurcation and saddle node bifurcations that give you the upper branches is something that you encounter in physical systems, and you'll see that in your exercise, I think, in a gene expression system. It's also seen in population models, and also, most interestingly for me, I think, in models of neurons and neural networks. So in neurons, usually X will represent some, maybe a firing rate. So then we don't have this whole region. We only have this branch and this branch. And there is a range of the parameter where there is bistability. And you can be either at a very small firing rate, sometimes 0, or at a significant firing rate, which will be a tonic firing.
So will it represent like the threshold between x to potential and
Yeah.
Before x that it will be like on 0, 0, 0, but after it will move a little bit above the.
Yeah. So if you give some external stimulation to the system, and you are here, if you perturb, you will usually come back to the fixed point unless you pass this unstable branch, and then you will go into the upper branch. So the size of the perturbation determines whether you will jump or not. Okay, let's take a break, say 10 minutes break, and come back.
איפה מגישים את התרגיל?
יש תיבה שם.
אז בקשר לתרגיל, בשאלה השנייה, אז עשיתי אותם לפי כמו שעשינו עם הדיאגרם.
אוקיי, כן.
ואז השאלה בקשר לאנליטי.
אנליטי, אתה רק צריך להגיד
באופן אנליטי האם יש סיבה או לא.
זאת אומרת, צריך לחשב את הנגזרת הראשונה ולבדוק אם זה לא.
זה לא ממש
לפתור את
לא תפסור את המערכת ממש לא.
ממש
לא. רק אם אנליטית פיקס פוינט אז הרעיון לא להימנע מדברים כאלה.
זה לא, כתבת אנליטית, אז
כן, כן.
סבבה, תודה.
טוב, אז בעצם פתרתי את המשוואה הזאת, דרשתי ש-x דוט יהיה 0. x דוט שווה 0 מתקיים בפיקס פוינט. אז כשאני כותב את זה, אני כבר יכול בעצם לסמן 0 שווה, אלא אם כן אין שום x שמקיימת, אז זה כמובן לא קיים ל-x כוכב. ואז לפתור עבור x. האמת שזה סוג אחד של ביפורקציה, אבל הביפורקציה הזאת יש לה x סטאר בריבוע. מה שמתאים לזה זה x כפול r מינוס x בריבוע, אז אחד מהפתרונות זה x שווה 0, והפתרון השני זה שורש r פלוס מינוס שורש r.
וגם לגבי זה רוצים שידעת עכשיו, זה מתחיל
לפה. כן, פה אני לא פתרתי את האנליטי.
זה השורה של מניחה
לא, אתה לא פתרתי. כשאתה מגיע כבר לנקודה 5, הרבה פעמים אולי אתה תצייר את המערכת, כן. מה שאתה יכול לעשות, בעצם אנחנו נראה את זה בשיעור הקרוב, זה לפתור עבור r. אז אתה מקבל r כפונקציה של x, נכון? אתה יכול לכתוב r x שווה x בשלישית פחות x בחמישית, ואז אם x לא שווה ל-0, אז r שווה x בריבוע מינוס x בריבוע. ואז זה בעצם לא, אז יש פה את העברת אלוקים מינוס x בריבוע, ואז ברור, פה זה מינוס x בריבוע ופה זה פלוס x ברביעי.
אז גם פה, אתה פתרת כאילו שני פתרונות, פעם אחת ש-x שווה 0, פעם אחת הפתרון של...
כן, אז אפשר להגיד, סביב x שווה ל-0, קודם כל יש לי פתרון x שווה 0 שמתקיים תמיד.
כן,
אז זה הקו הזה.
אתה לא מצייר, אבל
סביב x שווה 0.
אתה מצייר כאילו פשוט באיזה שתי... זה לא x באמת פונקט של r, זה פשוט הפתרונות כאילו ש-x שווה כאילו שמתחילים
כן, נכון, אבל מה שמעניין, מה שהוא שאל זה איך אני יודע את הצורות של העקומות האלה. אז ראיתי שאני יכול, אם קשה לי לפתור עבור x במשוואה כזאת, אני יכול לפתור עבור r, ואז בעצם לצייר את r כנגיד x, פשוט על הצד. אז r שזה מינוס x בריבוע, אז כל ליד x שווה 0 זה מינוס x בריבוע, אבל כש-x גדול זה הולך כמו r שווה x ברביעית. אז בעצם אני יכול לקבל את השורה הכללית בלי הרבה בעיה.
לכתוב משהו כזה. אם אתה רוצה, ניסינו שאני אבין.
זאת אומרת ש...
AX ועוד BX בשלישית, BX בחמישית. אם זה המערכת שלך, אז יש לך פה 3 פרמטרים. ואתה סתם, בחרת מקרה פרטני, שזה 1 וזה מינוס 1. ואתה אומר, יש לנו פרמטר כאילו...
אוקיי, קודם כל...
אתה יכול לחקור גם עם שתי אלה. פה, אם אתה תיקח את הפרמטר, תקבל איזשהו משטח, מסובך. עם 3 אתה כבר לא תוכל לצייר את זה. מה מיוחד בלבחור דווקא, כאילו... מה מיוחד בזה שבחר דווקא פה? את זה אמרת, בוא נבדוק את X של R, ולא דווקא של B או של C או של ככה של 3.
טוב, אנחנו מתחילים בקטן, אנחנו מתחילים בפרמטר 1. בשבוע הבא נראה מודל שיש בו 2 פרמטרים. וגם מה שאני עושה כשיש לי 2 פרמטרים ככה, הייתי מחלק ב-C את הכל.
למה כל הפונקציות שאנחנו רואים כאלה פולינומים?
יותר קל. שיש לך, בוא נגיד אקספוננטים, פה לא יכול לצור את זה מהלכים. אני יכול לצייר את זה בצורה ג'אומטרית.
אני מכיר כולה 3 תשתיות
כן.
טריגונומטריות, מערכיות ופוליניאליות. כל מה שאני מכיר. כאילו פונקציות בסיסיות. יכול לבחור ממש מסובכות גם.
אז 2 דברים. הפונקציות שאנחנו רואים הן פולינומים, בגלל שאנחנו הסתכלנו על נורמל פורם, על הקירוב ליד הנקודה הקריטית, וזה בפיתוח סלע הוא באותו פולינום.
אתה יכול גם לפתח את זה בבסיס פורייר.
אתה יכול, נכון.
אתה יכול בבסיס של הרמוניות שריות, אבל
כן,
זה נראה לי סתם.
אני
שואל אם יש איזה ייחוד לזה שאתה עושה את זה ככה הבסיס הזה, אם הייתי עושה על בסיס אחר, הייתי מקבל תוצאה דומה, זהה.
היית מקבל תוצאה דומה, הדברים האלה הם קטגוריות כאילו. זה העניין של הנורמל פורם. בעצם הפונקציה יכולה להיות גם עם פונקציות מערכיות וטריגונומטריות בפנים, אבל אתה תקרב אותה כרגע לפי טיילור, אז תקבל את הצורה הנורמלית הזאת, וזה סופר קריטי או טרנסקריטי.
גם בחרת שזה 1 וזה מינוס 1.
כן, וכשיש לי את 3 פרמטרים האלה, אני אחלק את הכל ב-C, כן? אז זה מיד הלך. פה אני אכניס את C לזמן שלי, לפי הזמן נראה את זה בשיעור הזה.
כן, זה דרך יפה להעיף פרמטרים.
כן, אז זה מה שנלמד עכשיו כשנחנו מהפסקה. אז זה 2 פרמטרים כבר יותר
ואז
חברים.
תצייר לא את X של T, אלא X של CT או משהו כזה, T של כ-C.
כן, ומה שיש, כאילו, אז מה שהראיתי לכם, הביפורקציה...
כן, אני יכול לעשות חוויות לכם קשה לי להוסיף עוד דבר.
נכון. הביפורקציה סולשון, מה שהראיתי לכם, אז נכון, היא מתקיימת אם אתה הולך רק לעוד פרמטר אחד, אם תצא מפה מהציר הזה שהקמתי אותך עליו, אז תקבל דברים אחרים.
כן, וזה כבר המשטח.
כן, משטח, זה נראה בשבוע הבא. פשוט תצטרכו לצייר בתרגיל, משטח כזה.
כן, וזה עדיין רק סדר ראשון.
כן, טוב, אנחנו תמיד נהיה בסדר ראשון. אנחנו יש ממדים.
מה זה ממדים? עוד בתיאס בו X דותיים.
לא, לא X דותיים. תמיד יהיה X דותיים. אם אתה עושה X דותיים, אז אתה מוסיף משוואה.
זה גם דרך.
So we are almost finished with everything I wanted to show you about bifurcations. There is one more thing that I want to show today about that, and that is what we do when we are interested in the bifurcation diagram, but we want to have an actual expression for these curves that describe the fixed points as a function of the bifurcation parameters. And I will just show here an example. We'll take, again, this example.
Can you write the topic, please?
The topic?
Yeah, what the topic?
Okay, you're right. This is very important. Bifurcation diagram. We are still in bifurcation diagram. Okay. So again, I want to take the system that I showed you last week of x dot equals a sum of some linear function in this. It's called it's a sigmoid. It can be called a logistic function because it's actually the solution to the logistic equation that we saw. If you remember, Rn times 1 minus n over k. If you solve this analytically, you get a sigmoid of this type. But so here, I just took the sigmoid because I want it to be part of my system. So we saw last week that this is hard to solve analytically, to find a fixed point. It's actually impossible to solve analytically. You must do it numerically. So what we do is we use a geometric method, and we say that, sorry, this should be a minus. We say that beta, it's a parameter. Of course, I could put parameters here as well.
So why did you put a minus the exponent?
Because I want the rising sigmoid, not a descending sigmoid.
Beta can be either positive or negative.
Yes. Okay, it doesn't matter. It doesn't matter, of course. You're right, it doesn't matter. I say that in order for this to be true, then I must have f1 equals f2, and then I can draw these two functions, one against the other. So this is just y, and here I have a line. I draw this with another color. So this is my f1. And then last week, I used a very large beta. I used beta equals 10. So I'll just draw for now with beta equals 10. Goes like this. This is f2 for beta equals 10. And then I have three intersections, and I can draw below this the phase portrait. I have three intersections, and the actual x dot is positive when f1, the line, is larger than the sigmoid. So it's positive here, and it's positive here, and it's negative in the other parts of the x-axis. So this is unstable, this is stable, this is unstable. The vector field goes like this. And this is my phase portrait, but this was for a very specific beta, and I'd like to know what happens for a different beta. So the effect of beta is to stretch the sigmoid. And specifically, we'll be interested in the slope of the sigmoid here at its intersection with the line. So I will take f2 and I will take the derivative with respect to x. This is equal to this expression. Okay, and I can take out the minuses, you just cancel out. And when we evaluate this at x equals 0, this is just, sorry, there was a beta here. This is just beta over beta over 2 over 4. Right? Yes, beta over 4. We did it last week. So we can have different situations based on the relative slopes of the sigmoid and the line. So the slope of the line is always 1/2. So beta over 4 equals 1/2, and then beta equals 2. Right. I'll try to draw here an illustration. So one situation would be the situation where the slope of the sigmoid is milder than the slope of the line. One half F1 F2. This situation will give us only one fixed point.
What situation? That of beta equals 2, you said?
Beta is smaller than 2, actually. So for beta smaller than 2, we have this situation. Now, if we increase beta, we increase the slope of the sigmoid until it will be larger than the slope of the line, and we'll be back at this situation. So you see 2 fixed points will appear. And this is a supercritical pitchfork bifurcation. And this is beta equals 2. Our critical beta is beta equals 2. Yeah? No, I meant her.
Maybe people that don't know the properties of the sigmoid, but I don't understand why the derivative at x equals 0 determines if the sigmoid will be above the line or below the line.
Okay, I'll present it like this. So beta here is a factor preceding x. So if beta will be 10, then if I have some, okay, the prototypical sigmoid, right? This one, okay? Okay, so if this is a prototypical sigmoid, if I have a factor preceding x, so this means that this sigmoid will be mapped to either stretched on the x-axis or shrinked. So if before x I write 10, then now x equals 1 will be similar to what previously was x equals 10. So the sigmoid will shrink, and it will be steeper. And now, if instead of 10, I write here 1 over 100, then now x equals 1 is the same as the previous x equals 100. So the sigmoid will be stretched. And the slope was a kind of indicator for the relation of the sigmoid with the line. So I want to know whether the line and the sigmoid can intersect in 1 point only or in 3 points. So for a very mild sigmoid, they can intersect only in 1 point. But a steep sigmoid will look like this, and then it will have to cross the line again here and again here.
But
So
also,
there will be 3 fixed points.
if it's a little bit, like beta is beneath 2, but very close to 2.
Very close, yeah.
It can, but the slope of F2 grows. So if at the beginning it's beneath this, it's going may cross and
Yeah, so the
So
crossings
we'll
will
have
be
to-
very close apart.
what?
You will always have either 1 or 3 crossings.
Yeah, but so for beta smaller than 2, we might have more than 1.
No.
Like, you know.
No.
Right, but its
okay.
slope grows. I mean, of F2.
The slope for beta, very close to 2. The slope will be very close to 1/2, but it doesn't matter. You can draw it later in MATLAB or whatever function and check. I want to move on, and having found with the geometrical method that it's a supercritical pitchfork bifurcation, now I want to have the exact expressions for these curves. So one thing I could do is to set x dot equals 0, right? And try to solve for x. Again, not possible analytically, but you can do it numerically. So you can solve for x for different values of beta, and then get numerically these curves. But a useful method in such complicated situations will be to solve for beta. And then instead of plotting x as a function of beta, plotting beta as a function of x, only sideways. And in this way, get the bifurcation curve. So this is, of course, much easier. So I'd like you to note that first, my solution will not include x equals 0, but I can deal with it separately. So x equals 0 gives here 1/2, and also 1/2 here. So beta can be anything. So one curve that comes out of this is that for any for x equals 0, beta can be everything. This is this line of the pitchfork. Any beta. This is on a side note. Now I can try to solve for x from here. So if x doesn't equal -1, then I can divide by 1 plus x. And I just pass things around. And I get 2 over 1 plus x, right? Yeah. And then I pass the 1 from the left side to the right. I take the logarithm with the condition that x is smaller than 1. So minus beta x equals natural logarithm 2 over 1 plus x minus 1. and then I divide by x. I already dealt with x equals 0. I divide by minus x equals 1 minus 1 over x times the logarithm. Yeah, there should be that condition. X larger than minus 1. This here? Okay. Okay, so if I plot this function, basically get this thing, and this will give me the exact expressions for these curves.
Why x has to be
Smaller than 1. If x equals 2, you have 2/3 minus 1. Okay.
Why does it need to be larger than minus 1?
Let's say that x equals minus 2. So no, so yeah. Okay. Okay, so this is a very useful method. Sometimes you want to get exact plots of the bifurcation curve, and then predict. One thing you can predict with it, for example, is out of my own research, the firing rate of a neural network as a function of the background input. So then beta would be a background input, and then you want to know what is the stable firing rate of the neural network for each value of external input. I'm moving on to the next topic. I'll write down the topic for the guy who, your name? Done, right. So I'll write down the topic.
The right graph is for any beta?
This?
No, about?
This?
Yes.
No, this was for a specific beta.
What is the difference between?
This was for a beta that is smaller than 2, and this was for a beta that is larger than 2. Okay, the next topic is dimensionless analysis. Dimensionless. Analysis and scaling. A lot of the time when we deal with dynamical systems, it's very helpful to try to take away the dimensions. And it can serve several purposes. So first, simplify mathematical analysis. If you are trying to find the fixed points analytically and to define their stabilities analytically and to find these curves, a lot of times the dimensionless analysis will take away some of the parameters, and your equations will just look a lot nicer, and it will be a lot less confusing. Okay, like I said, reduce the number of parameters and parameters. I talked about this with Chagai during the break. In principle, you could have even this 2 as a parameter, say gamma, right? And you can add here parameters all around the equation. And then your fixed points and their stabilities will depend not only on one parameter, but on many parameters. So there is a question of what's the minimal number of parameters that we need here in the system. We'll try to group all the parameters together. You'll see it in the example. and remain with a minimum number of parameters, hopefully 2. And another thing, neglecting parts. So you might have several parts in the equations, and when you do the dimensionless analysis, it's a lot easier to see which part should be larger than the other. Usually we talk about larger by orders of magnitude. So we might say, oh, okay, but we know beta is the physical constant describing the amount of resources in the environment. So we know this is very big, and so the term that includes beta can be neglected with respect to all the other terms because the constraints of the environment are not actually felt. So sometimes you'll be able to know which parts you can neglect. Okay, these things are a lot clearer in examples. It's really hard to talk about this in an abstract way. So I'll just start with the example. I return to the logistic equation that we saw last time. N dot equals Rn times 1 minus n over k. And I want to bring this equation to a simpler form that will also be dimensionless. This form will be dx over d tau, because I'm not even constraining myself to using the real time axis, equals x times 1 minus x, which is, this form is actually what we used in the very first lecture as an example of the geometric method. So this is kind of arbitrary, okay? I can devise maybe a different form. Maybe I am willing to settle for b times x times 1 minus x. So sometimes the simple forms that we want to get to will be arbitrary. A lot of times you will be, in exercises and questions, you will be given this form and asked to reach it from the original system. Sometimes there can be several simple forms that you can choose. And maybe they're all useful, maybe some are more useful than others. The first thing I want to do here is to look at the dimensions of the parameters and variables in the system. So this is actually dn over dt. And the way I write this down is I write the variable or the parameter in square brackets and then write its units. So the square brackets are kind of stripping it of its value and just giving me the units. The units of population, it's just individuals. It's basically unitless. But you can invent your own units, okay? So I can invent a unit of individuals, a unit of hundreds of people, thousands of people. So let's say I want to use 1,000 people, so I can write kilo and I make a sign of a person, right? There. Just a unit I just made up. This is the units of n. The units of t should be units of time. It can be seconds, it can be hours, it can be years. Now, the units of r. In order to do this, I want to discuss for a minute kind of the rules of using units. When we have any equation, the units must cancel out on both sides of the equation. So on this side of the equation, we have our kilo people over years, okay? On this side of the equation. On the other side of the equation, we must have the same units. We cannot compare quantities which have different units. You cannot say that 3 meters are equal to 3 seconds, right? It makes no sense. So on this side of the equation, we must also have the same units. And in the parentheses, we have a number without any units. So these parentheses must have no units. Also, when you add or subtract quantities, they must have the same units. Okay? So this means that the kilo person per year must be balanced by this term outside of the parentheses. This is in kilo person, so this must be in 1 over a year. 1 over years. So I got the units of R. Now for the units inside the parentheses.
1 person per year.
Yeah. No. Per year. This is just a rate. R. Not Rn. Now for the parentheses, I said they must be unitless, dimensionless. So this means that K must balance the units of N. I divide N, and I also divide the unit of kiloperson by something, so it must have the unit of kiloperson in order to be able to be subtracted from a number that has no dimension. So K is also in kiloperson. So I got all the units. And now I want to start the process of non-dimensionalizing the equation. Today I'll show you one tactic to do this. And in the next lecture, we'll see a different tactic to do this. There may be several ways to get from here to here. And it's a kind of it's a kind of heuristic process. It's something that you can try and fail and try again. Just search for the better way. There is no specific way to do this. The first thing I want to do, the first thing that is commonly done is shifting the time scale or stretching the time scale. So instead of talking in years, I would like to talk in a time scale more relevant for my system. For example, if I'm talking about the decay of a radioactive isotope, it will be easier for me to talk in time units of half-life of this isotope instead of talking in units of seconds. Okay, it will. You'll see that it takes out a parameter of the system. So now, if we imagine n as a function of t, we can say that we are starting to talk